That was great. So at the end of your talk, Noel, Jack leaned over and said, you're doing geodesign at the global scale.
Yes.
And
it's obvious, isn't it? I mean, it's not physical design, but it's policy design, where you're saying if we do this, these are the consequences, and you're driving it to local.
Yes.
To local. So that kind of systems model
right.
Is the underpinning for global geodesign.
Right.
Yeah, I get.
So that's the link. The link is through uncertainty. That PCTM model, you know, at scales of 100 kilometers, but you really want to know from a policy point of view at much finer scales.
Yes.
And through the construction of these probability models, you get to know it. We're actually doing a little more with that particular process because we artificially put satellite tracks on top of those maps that you saw. And so we add the missingness and the imperfection of a satellite in order to say how well our remote sensing is going to do under certain scenarios. Because ultimately, it's the satellites and the data which is going to determine whether these policies are actually working, not a parameterized chemistry transport model. So the systems model allows us an inroad.
The uncertain part of this model is that you depend upon policies at a national level.
Yes.
Because if you drove it from that policy, which is political sort of rhetoric, down to the human action, like, do you develop something here? Do you, in a way you have to sort of drive it up. Forget about policies because it's political bullshit in a way. But if you drove it to human, I'm just repeating my saying, so that it's transaction, and you aggregate the transactions into quasi-policies, and you don't do it by nation states, but you do it based on your hierarchical grid.
Right.
Because what happens is that people make action. Countries don't actually make action. And those actions are geographic. And they are the sort of design action aggregated up. Right. So ultimately, like Singapore showed last year at the users conference, they said if I put this building here, they ran a model and it showed how it increased traffic throughout the whole of Singapore. Right. It wasn't just traffic right around the building, it was modeled out. And you've sort of laid out a framework where
we can aggregate and disaggregate.
You can aggregate and disaggregate.
And you've added that extra dimension, which is stuff happens in the trenches. And what are the consequences of that to a region and the consequences of that regional variability to the national variability, or even to the global variability, for sure.
We pretend in a way to be conscious enough to know that this, putting your footprint here, will have different effect than there.
Yes.
In a way, it's sort of out of control.
Yes.
I mean, it isn't sort of out of control, it's totally out of control. Yes. But where can we guide it using geographic information?
Yes.
Yeah. That's contextual, but I'm also, contextual conversation, but I'm also just totally enamored with this notion of how do we drive spatial statistics into the behavior of Carl's. I mean, do you have any thoughts on how you could? Okay, well, why don't you talk about it?
Lots of them. Noel and I have communicated by email for the past couple of months, irregularly, but we only met on Tuesday for the first time. And there was a very small group of people who were there, and it was a really, really interesting conversation. Allow me about 5 minutes?
Yeah, go for it, man.
My first studio project in graduate school was to double the size of Washington, D.C. Okay, so nothing small. Nothing small by my scale.
Right.
In the 1960s, I was a master's and doctoral student at MIT. And everybody was interested in the failure of Moscow to control its growth. Moscow was a communist state, central control. They had every law you wanted to have. They had all the police power you wanted to have, and they couldn't control the growth of the city. And there was a literature in the early 60s, late 50s, early 60s, that basically said master plans are out. Why? Because they presume certainty. Now, there was a general agreement on that. I mean, I was taught master plans were out, except for two people. And I find these two people to be really, really interesting. One was a professor, Tom Adams at MIT, a planner, an urban planner. And he said, no, master plans are not out. What's wrong is your conception of what the plan is. And he said there are some things where you need them, like general hospitals, sewer systems, road systems, water systems, dams. And for those you're looking 20 years ahead, you have to plan them, you have to finance them. But housing is stochastic, the little houses that are spread out. Farming is stochastic. And so what you really need to do is divide the world by time and say these functions are in a master plan, these are not in a master plan. And I thought that was very interesting. The other person was Kevin Lynch, who was my mentor. And Kevin Lynch said, master plans can't possibly control everything. So make your design adaptable. He wrote a brilliant paper, which I quote a little bit in my book, called Environmental Adaptability. And he said, these are the principles of physical design at all scales that basically say it can adapt to different conditions, different spatial needs. It can grow this way, this way, this way, this way. And I wrote a paper in 1960 called In Defense of Urban Sprawl. Why? Because it's physically adaptable. That's why. Right. So this idea that there's randomness and uncertainty are necessary, I think is very powerful. Okay? Secondly, there really is a difference between policy, and I call it policy and projects, which I've built into this system we're dealing with. Where policy is a guideline and a project is an action, which has a cause, effect, a price, et cetera, et cetera, et cetera. Okay. So I think that that combination of stabilizing things and randomizing things is really, really important. Now, what are the stabilizing things? The stabilizing things are probably things like major transport, major water, major sewer infrastructure, and I would add landscape. Getty's idea of the landscape structures of the city is really important. But what are the others? They are shopping centers and housing and the ubiquitous development that really probably is the great cause of some of the things you're studying. Okay, that's the second thing. The third thing is your scale 6, the map you have at scale 6.
Yeah.
At the Center for Advanced Spatial Analysis about 4 or 5 months ago, there was a lecture by one of the people who used to run the transport lab at Berkeley. And he made the following statement. He said, the World Bank thinks that more than half of the growth in the next 20 years, urban growth, is going to be in cities of 1 million growing very, very fast, 1 million to 5 million. Not in the megacities. And what he said is, as a transportation planner, it's almost impossible to plan a city greater than 5 million. So I think that and that's in your resolution 6, I think. I think a resolution 6 thing will say, I'm making up a number. There are 500 cities of 1 million people. Let's assume this in the world. Maybe 50, I don't know. I tried to find out. And those occupy half the growth that's causing the problem. They're at your scale 6. They're in different cultures. That's important. They're in different geographies. That's important. But they're all going from 1 million to 500 million, and if you don't plan it then to grow to 10 million, you're screwed. All right. Strikes me that that's an experiment. Right? You find those cities, you randomize the selection in your model, and you say, now what? Well, now what is you need a set of tools, which I think are beginning to be available, to say, well, what if we design the infrastructure, randomize the growth, and run an experiment on several infrastructure patterns, randomizing the growth, and see if it matters to your model, because you're dealing with delta. And that's probably the single, maybe that in agriculture or forestry, are the 3 land uses that, it's like Juan Carlos's thesis, it's urban, agriculture, forestry. Model those processes, and you'll see if you actually might be able to control the carbon cycle. Right. But if you don't do the stressor test, and I'm the stressor, okay?
Yeah.
You're the test, I'm the stressor. If you don't do that test, you don't know how to move into policy.
Right.
It's the city as a kind of plot.
Well, the city, see, the
Yes,
forestry industry, the
Yeah.
agriculture industry, and the city industry.
Right,
Right.
right, right.
So you
And
can model-
you basically model an experiment that sees if we can stress less
Right.
your system by the kind of policies at scale. And frankly, most of the work that most geodesign is the problem, not the solution. It's a symbol of the solution. But if you've got only 10 years to figure out what the real solution is, you can't screw around with little things. You have to think about strategy.
So what you've done is really describe what I've really been working with over the last 10 years in the environmental arena, where you don't get the opportunity to run a well-designed experiment that Fisher did. You're in what could be called an observational studies mode. But what you've done is describe blocking, which is the infrastructure.
I know I have. I made
You've
notes.
described
I made those notes. I
randomization.
made
Yeah.
exactly those
Yeah.
notes
Yeah.
on my page when you were talking. That's why I like to talk.
Right. And the replication aspect, thank you. So we have a language that actually is common. It's just that we need some translation. That's why we're here. That's great. And so in my work in the last 10 years is to help design not only the collection of the data, which is clearly never going to be able to be replicated because, you know, the world is in a sense one replication, and from that point of view, but to try to design it so that we get pseudo-replication. In a spatial context, you do get pseudo-replication. And in that design, you do get a chance to choose not every city, but choose some of them, and there's the randomization. And the blocking, of course, is different cities because of their physical aspects.
Or
behave
their
differently.
political system.
Yes, or the political system, precisely.
You know, Carl, you ran these experiments at all different scales.
Yeah.
If you ran a global scale and Noel's models were running in the background, you might ask, we have 5 different choices for urbanization in the future. Megacities, less than 5 million cities, 1 million population cities, maybe those are the 3. And we say, we're going to continue urbanizing, and we'll just say, we'll use Roger Sayers' map of the world to pick the right places for the cities using geodesign.
The Chinese have gone through that experiment.
And then run it through Noel's models to say which one results in more or less, impaction in climate.
Right, and with a certain probability.
With a certain probability.
That's the point, is that the washing of these Bayes rule, in a sense, the washing of the posterior probability of the thing you're interested in, given what you've observed, on top of these concepts, Jack, that I really I'm not the expert on, but the point is we can't always be experts in everything, and that's why we work in teams. But this notion is really quite generic and can be washed in many ways across sorts of questions that you want to ask, which is, we really do want to design our world. If things happen haphazardly, maybe we're at the 1% chance of surviving. If we get involved, we can increase that probability beyond 10 and into maybe get it above 50. But we need to do that intelligently and in an era of uncertainty, as well as an era when we have a chance to make a difference.
So underpinning it is global databases with global synoptic measurement, with models that look at the implications or the evaluation steps 5 in your set, and then we need creative formulation of these scenario sizes of cities. I mean, Paul Farmer is here, right? Yes, Paul, I mean, wouldn't your people like to know that we should take this approach or that approach with urbanization? I mean, wouldn't that be a kind of thing that you could get behind?
From the American Planning Association point of view.
Sorry.
Yeah.
I mean, I think absolutely yes. Anytime you get the additional kinds of analyses that are being talked about, then I think you've got a situation where people are going to figure out ways to make better use of that at the local level or whatever decision-making scale they're at. So absolutely yes.
I mean, you take something like China, they're making decisions at this mega scale. Do we grow Beijing and Shanghai.
The answer is no. The answer is
or
string of cities that are smaller and linked by fast trains.
But yet they're doing it without the
right.
the evaluation of knowing
right.
really what that policy is.
You're right.
So if nothing more, this kind of a scenario for the world could give guidance to those states or those nation states that actually could drive policy, and you could do it through professional associations like Paul really runs. I mean, to me, this is interesting.
Other questions from the audience or thoughts? I want to bring you in here. No? Oh, yes. Okay. Yeah, Mike.
Do we have runners with mics? Yeah. One runner with one mic, is that it?
Yeah. It's a lot of running.
Yeah, right.
Yeah, it's very Bayesian here.
Yeah. Somebody in the AV area, get on it.
Go ahead, Mike.
So I love this conversation at that scale, but I want to bring you down one scale. Yeah, I think all of what you just said is true and incredibly important. But when Carl and I, for instance, have done studies everywhere, the startup discussion usually is a big whiteboard and what we call the system of systems diagram. And we try to figure out which sets of models are needed and how those can be chained together to get a useful simulation result. And the elephant in the room is the propagation of uncertainty between those models, which is something, frankly, we have not treated well, in part because there aren't good interdisciplinary methods for treating that. And I was wondering if you had any reflections on how to apply this kind of framework to situations where, I'll give you a tangible example. I'm studying the Florida Everglades. Michael Mann is doing the climate change modeling. We have great hydrologists routing the water through a complex human design network. And we have a series of ecosystem services models trying to describe where that water is needed and what its benefits are for people, nature, agriculture. Each one of those models has enormous uncertainty bounds.
Sure.
How do you assemble geodesign tools that are able to deal with uncertainty across and between models, not only between scales, as we've been talking about,
right,
but between chained models?
Sure. I did give some mention to the fact that, you know, everything's related to everything else, and what you're describing is what often scientists now deal with using systems models, which means they run a model with deterministic input, forcing factors, which they simply put in from guesswork, and the outcome at the end is something that is totally deterministic. In other words, when they ran it again, they get the same answer. So when the hydrologist puts in information into what goes into the water table, and when someone else puts in some climate information, there's some general feeling about how those two are related, and they're often quantified by algorithms within a big systems model. And I've dealt with these in my work with, I'm interested in carbon and carbon dioxide, and I've worked with people in the CSIRO that run big systems models on sequestering carbon in soil. And as most of you probably know, there are different pools of carbon as to do with their decay rates. And what we have are models that you might call FullCam and Rothsey, if some of those names are familiar to you, which simply do what I describe, where soil properties and climate properties are involved in the running of that climate model. And what we've done with CSIRO is put the uncertainty in through these hierarchical models. So now we can output where the carbon, how the carbon is being sequestered and why it's being sequestered using particular crop rotations, and the probability that the carbon is being sequestered, that it's a sink and not a source, and we can actually quantify the uncertainty based on it. And our goal, and I think you'll like this in the geodesign community, is to give the farmers, the people with the boots on the ground, the ability to farm carbon and know what its value is or what its worth is. And that ability to farm carbon is involved with a distribution function. Like the probability if you do this crop rotation, probability that you will sequester so many tons of carbon is higher than if you do another crop rotation. It might be wheat, or wheat fallow. I mean, that's the sort of work that we're now doing, is getting to decision tools. This is my goal in my career, if you like, is to make a difference, but also to get to a point where I'm making a difference, not by handing off politicians or management people who will throw away my variance estimates and take my means and not deal with the variability. So what I've tried to demonstrate through my work at JPL and through this small anecdotal example that I'm talking about is that you can get all the way into decisions if you do the probability modeling and the uncertainty modeling. And if you've not heard of this before, it's because it's new. I mean, these ideas, the ideas themselves are probably 10 years old, but the implementation of them are 4 or 5 years old, and the publication of them is 2 or 3 years old. And my talking here is 45 minutes old, you know. Yeah. So what I'm trying to do is really indicate to you that there's a revolution out there which is gaining steam. And the reason is because we can answer questions in the presence of uncertainty, and we know the world is uncertain.
Well, to stay on time, I know that's certain, we're going to need to take a break. So thank you, Noel and Jack and Carl, and to be continued. So get back here at about 10:45. Thank you.